So our next video is going to be an introduction to Boolean algebra focusing on basic theorems. You will hear new ideas or concepts like identities, the null element, idempotency, involution, and complements. Then we're going to focus on theorems that involve 2, 3, or more generally n variables, and perhaps the most important thing from this series of from this week's lecture, is going to be DeMorgan's theorem, which is very important and which is something that you should pay particular attention to. So let's start. We're going to see a series of operations with zeros and ones. The first one is identities. Let's check out these two first theorems, identities and the null element. If you're having a logical OR and you are using 0 as the second operand or as the first operand, the result is going to be the same as the other input variable. Now, there is a dual to this theorem for the logical AND. Only in this case, the other input should be equal to 1. Focusing on the second theorem, which is the null element, you see that the null element for the logical OR is 1. And that means that if you do a logical OR between 1 and any variable, the result will always be 1. So essentially, this is a null element. It doesn't change, it enforces the result. It's not dependent on the other input variable. And its dual, when it comes to logical AND, is by using as our second input over here the logical 0. Now, if you pay attention, you will realize that from the first and the second theorem, we can extract one thing in common, and that is that if you have one theorem, then it has its dual for AND. If you have one theorem for OR, its dual for AND is by using a different symbol. So for identities, you're using 0 when it comes to logical OR, and then you're using 1 for the logical AND. And the other way around here for the null element when it comes to the OR operation is 1, but when it comes to the AND operation, it's 0. Idempotency. What this says basically is that if you're using for the operation the same variable, then of course the result will be the same at the end, and its dual is exactly the same. Then we got the involution. If you use the complement of the complement, you will get the same result as the variable. And here we got the complements. If you do a logical OR between a variable and its complement, the result will always be 1. One of them must be 1. This is why. Now, its dual makes the result equal to 0, because at least one of them is going to be not true. So as we said, to obtain the dual version of a theorem, you just replace AND by OR the other way around, and then you replace 0 by 1 and 1 by 0. Now, as you can see, these theorems are very basic, very easy, and there is no need for you to remember them by heart. You just need to understand the reasoning behind it. And if you can do that by using reasoning with switches or truth tables, this is more than enough. Once you know a theorem, you deduce its dual counterpart, and everything is easy. Let us focus now on how you would depict that with switches. Let's start with the identities. Well, as you can see, x plus 0, if you put them in parallel, is essentially the same as having x, which is why in an identity you will get as a result the input variable itself. Now regarding its dual, think of it, if this is always equal to 1, if the circuit is always closed, then everything depends on x, which is why the result is x. Essentially, it's like having only one switch. Now, let's think about the null element. I challenge you at this point to pause the video and think how it would look like based on the former example. Take this as an example and try to think about the null element. Again, we assume that we have two switches in parallel. One of them is always closed. So it's like having always a closed circuit. But regarding its dual, then you probably thought of it correctly. It's like having always an open circuit. So the result is always going to be the logical 0. Now think about the idempotency. Remember that this means that you are doing an operation between one variable and itself. Wouldn't that be an equivalent of this switch over here having only x? And again, exactly the same thing if you put them in series for the AND action. Regarding the complements, which means that you're doing an operation between variable x and itself, or and its inverted self. Well, for the OR action, the result should be 1. This is very easy to understand. Either one of them is going to be always 1, so essentially it's equivalent to 1. While for the case of AND, one of the two is always going to leave the circuit open, so it's essentially like a circuit that never closes. So let's start. Now let's see a little bit of more complicated theorems, including 2 or 3 variables. The first one is called commutativity. As you can see, commutativity means that you reverse the operands. So this is for the OR, and this is its dual for the AND. This is pretty straightforward. It's very easy for you to understand. Now let's see associativity. This is a little bit more interesting. So x plus y, if you put in a parenthesis, plus z is equal to x plus, open parenthesis, y plus z. And as you can see over here, it's exactly the same diagram of switches. When it comes to associativity for the AND action, again, it's very straightforward. No matter how you interpret it, on the left or on the right side, the circuit is always the same. Now, let's leave the switches behind and let's move on by using the logical gate symbols. This is how you would depict associativity. You would have an OR gate over here for the parenthesis, another OR gate here for the result of the parenthesis plus z. And as you can see, of course, these two are equivalent. If we want to save space, you can use the symbol of the OR gate with 3 different inputs. And exactly the same concept applies to the AND. As you can see, you got 2 AND gates here. The first one groups together whatever is in the parentheses, x and y, times z, and of course these two are equivalent. And you can do exactly the same trick again. In order to save some space in your diagram, you can use an AND gate with 3 inputs. Distributivity. Now that is something which probably rings a bell. It's like those very fundamental, simple mathematical operations that you're familiar with since high school or even primary school for some of you. So x times parentheses y and z is obviously equal to x times y plus x times z. So if this is a switch for x times a logical OR here, which, as you can remember, it should be like having two switches in parallel, and all that is equivalent to having this. X times y, x times z. If you put them in parallel, it's like taking the logical sum of the two. This is the truth table. Take a moment to pause the video and check out how it looks like. Now let's check its dual, the dual of distributivity. Only this time the operations are reversed. X plus parentheses y times z. As we said earlier, if you want to have its dual, then you replace dots with pluses and pluses with dots, or in other words, ORs with ends and ends with ORs, and you get the result that you want. This is the equivalent in terms of switches. So on the left side you got something like this. It is x or whatever is inside the parentheses, and that is a logical AND, so they have to be in series. And if you think of it, this is essentially the same thing as what you have here on the right. Something that you can verify with the help of this truth table. Covering. Let's focus on covering now. As you can see with covering, if you've got one variable in both sides, you've got an OR operation, then x essentially covers y, and the result is an x. In terms of switches, this is what happens. Because of the OR action over here, everything depends on the x. Now, regarding its dual, things are again, there's again an equivalent way of thinking. If you convert that in terms of switches, you will realize that because you use x in both sides here, in both operations, then x is covering y. And this is because the result will always be dependent on x, which essentially makes it an equivalent to a very simple single switch element like this one over here. Let's turn now to combining. Notice that in this operation, this OR operation, you got y on one side, and then you got a negated y on the other side. As a result of that, everything is dependent only on x. If you draw this in terms of switches, you will easily realize why. Either 1 of y or y prime, in this example y prime, is going to be 1. So the result depends only on x. By the way, this is something that you can also prove with theorem number 8 that we previously explained. If you remember, we call this theorem distributivity. Now, again, another example of combining variables. In this particular example, we use the AND operation. This is why we say that it's the dual to theorem number 10. Again, if you draw the switches, you will realize that because of using y on both sides, only on the second side being negated, everything depends on the x variable. So if y, for instance, is 0, like it is in this example over here, it will definitely be 1 here. So at the end of the day, everything is equivalent in a series of x's, or if you want, just a single switch for x. And that can also be explained by using the distributivity. Now let's turn to consensus, which looks slightly more complicated, but the way we're going to approach it is going to be easy for you to understand. So x times y and x times y plus x prime times z plus y times z should give you the result on the right, which looks simpler. And we call this consensus. Let's try to approach this by using switches. Just notice what the result would be if you just got rid of the black part over here, which is y times z. Would it be different? Actually, this part doesn't play much of a role. If by using switches this is not enough for you to understand why we have the consensus theorem, then we can actually prove it by using a series of other theorems. So let's start with the identities. In order to get rid of it, we logically multiply by 1, and the result shouldn't change. And then we apply theorem 5. Theorem 5 is what we call the complements. So 1 is equivalent to x or negated x. That would always give you 1 as a result. This is also straightforward. And now we're going to use distributivity. So by using distributivity, the result then on the next line is what you see over here. Now pay attention at this point. Because of commutativity, or otherwise called theorem number 6, on this line you got x times y plus x times y times z plus negated x times z plus negated x times y times z. So far we started from here, and we ended up, after using these theorems, to this line over here. Again, if we use distributivity, the result takes the form that you see over here. And now this is very easy. Because of the null element, remember that 1 plus z will always give you 1 at the end. The same as here, 1 plus y will always give you 1. You end up in this line over here. But then again, because of the identities, we end up in this simplified form. So consensus is nothing more than applying a series of the basic theorems that you saw earlier. What you need to remember, if you have 3 variables, and these variables have all the possible combination of ends by using pluses between them, then the result is something more simplified, and it's equal to that. And of course, there is a dual for the consensus as well. I believe that this is more straightforward to understand. Just notice the result over here. Again, you do not need the last part. Everything depends on the former two. And as we did in the former slide, you can start with identities the identity for the logical OR is 0. Then by using complements, we can replace 0 by x times negated x, because this is always equal to 0. Then by using distributivity, you can convert that. And the result of the conversion will be this one over here. Just pay attention to how we apply distributivity in this case. If you find distributivity confusing in this case, remember that try to approach it the other way around. If instead of pluses you had dots, and instead of dots you had pluses, if you approach it this way, you will realize that the result is going to be that easy. Then we use commutativity, just to put the variables in the order that we wish to have them. And then again, distributivity. And at the end, we use the null element. Which leads to the final desirable result over here. So unlike the fundamental easy theorems, perhaps it's advisable to learn the more complex one, like consensus by heart. And let us switch now to the most important and most interesting part of this lecture, which has to do with DeMorgan's rules. Again, Augustus De Morgan was a British mathematician, and his theorems have to do with n-variable expressions. So let's check this out. Pay attention to what we have inside the parentheses. We have a series of n's. We got n variables, and then we invert the whole of the result. According to De Morgan, if you invert the result of a series of n's, it is the equivalent, or if you want it's equal, to a series of ORs of the inverted variables. And this one has a dual itself. Now, if you invert a series of ORs, as you can guess, the result is going to be a series of n's of all the variables inverted. Take 1 minute to take a look at both De Morgan's rules. They're very easy to understand and very, very important. Now that you've taken a look at De Morgan's theorem in both ways over here, let's see how you apply it on this example. So if x and y is equal to z, according to De Morgan, if you invert the left part, which of course, as you know, should be equal to the inverted result z, that would be equal to the OR operation between the inverted x and the inverted y. And you can verify that this holds based on the truth table for any possible combination of x and y. Now again, let's see De Morgan's rules, this time by using gates. If you have a logical end, in order to invert it, you need to put a complement gate exactly after the end. Now, according to De Morgan's rule, this is an equivalent of having an OR gate where you have inverted both of the inputs. So if we use something which is shorter to symbolize the AND gate, we also call this the NAND gate. That would be equal to this gate over here, which, as you can see, it is an OR gate with both of its inputs being inverted. And again, De Morgan's rule, only this time a little bit different. In this case, we have an expression which starts with an OR over here. If you get this OR and you invert it, the result would be an AND gate where both of its inputs have been inverted. And as you can guess, we take the symbol over here, which is an OR gate negated with a negated result. We also call this a NOR gate, and that is an equivalent of an AND gate where both inputs are inverted. And by this example over here, you should start to understand why DeMorgan's theorem is very important. Let's see what we got here. We got this function which has several variables as inputs. It has n variables, as you can see, and it has some series of ORs and ANDs. Now, if you invert the whole of it as an expression, what you get is again the same function, but all the inputs are inverted, and all the OR operations have been replaced by AND operations, and all the AND operations have been replaced with OR operations. If we take this example over here, and you follow these rules, you will end up in something like this. All the variables are inverted, all the gates have been switched from AND to OR and from OR to AND. And of course, don't forget that the final result, which is the result of the function, is also inverted. Now, if you're wondering why the generalized De Morgan is important, the answer is pretty straightforward. It's because it simplifies Boolean expressions, and this is something that we're going to see with a series of examples later on. And as we said earlier during our introduction, by simplifying Boolean expressions, you make your logic circuits more efficient in terms of power consumption, number of gates, and speed. If you think of it, all of these three aspects over here, power consumption, number of gates, and speed, they're closely related. The less the number of gates, as you can understand, the faster the circuit is going to be because the current has to go through less gates. And of course, power consumption will be lower in this case. So remember that De Morgan is the most important, De Morgan theorems are the most important out of what you've heard today.